All right, let's get started. Good afternoon, everybody. Welcome to cloudy and sometimes rainy Thursday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. That's better. Now my glasses are properly aligned. I can see better. And hello. All right, important announcements. First of all, after class today, I will be sending out the password for test number 3, and you'll get it. Hopefully, you've downloaded. If not, download the test number 3 PDF file and use the password. Open it up, take the test. If you need it more than an hour, that's okay. I think I pushed that, take up to an hour and a half, and then upload it by the deadline tomorrow. I think it was 11 o'clock or 10 o'clock, I forgot. By tomorrow morning, upload it and I will grade it. Now, I should mention tomorrow I have some personal stuff that I'm going to be busy all day. Normally, I grade tomorrow. So, listen carefully. I promise, not guarantee, promise. And so far, I've never broken a promise in my life to myself or anybody else. That's just who I am. I promise by 8 p.m. Sunday, your test number 3 scores will be in not Blackboard, wrong school, in D2L. And also by that time, I'll have emailed out your individual points for each question, and you'll each get an individual email, just like I did in test 1 and 2. And I hope to get it done earlier, but let's see how late I stay up Saturday night doing grading tests and other things. Because in the class I teach at another school, about 2 hours ago, I gave a test, so I'm going to be busy Saturday grading. Lots of tests. I figure it's going to take me a while. Never mind. All right, that's one thing. Another thing is I got a special gift for you on Monday. Special gift. Over the weekend, I'll post it in the assignment area. It's optional, but I'll talk more about it on Monday. Also on Monday, I will go through test number 3 answers, and I will cut it out of the video. But if you can't make it to class, come to my office hours, or if you can't come to my office hours, email me, and I'll find a way to set up a Zoom meeting so I can get you the answers. All right, let's see, I've done that. And uh, by popular request from one of your colleagues, if you notice earlier today, let me open it up because I don't have it open. A little earlier today, I was thinking about it. Not everybody shows up to our lecture, and they don't have to because this is an internet. Hold on. All right, now they're aligned. Test, ketone. It works now. All right, this is an internet course, not a VCM virtual classroom meeting class. So you don't have to. And the way I set it up this semester, summer, is I'm treating it like a VCM in terms of lecturing, the same as if we were at face to face. But I'm also, for those who can't come here, I'm posted on um, YouTube. Now, what I sent out this morning was the following attachment to an email talking about common mistake from test number 2. And as I mentioned when we went through it, if we look at the following problem, which was on test 2, this alkoxide plus this alkyl halide to make this ether. Here's the general reaction. The carbon with the halogen is the carbon that the oxygen is bonded to. Now, what students did was this a number of times, and it's wrong because this oxygen is bonded to this carbon. And let me get my pen out. Oops, got to fire up my tablet. I had it off. All right. By the way, thumbs up, people. Do you see that file on your screen right now? Thank you. My morning class, I had the slowest ever I've ever had thumbs up, people. But they're doing good, so I'm happy. It says, why is this wrong? Because this oxygen, the way drawn, is bonded to this carbon. It shouldn't be. It's supposed to be bonded to this carbon. And therefore, it's wrong. These are different molecules. In fact, this one can't exist. Why? Because this carbon has 5 bonds to it. No way. You show me how to get 5 bonds to carbon, 5 covalent bonds, and we'll be rich beyond my wildest dreams. And that goes beyond having my own Lamborghini and Countach, or Lamborghini Countach, and my Ferrari. And it also goes beyond having my own islands in the South Pacific and my own toy fighter jets to play with. No, it can't happen. And at the same time, this carbon has 3 bonds to it. It can't. Now, let me show you what I mean by proper placement. Because I say here, it's critical that you bond correct atoms in one structure to correct atoms in another structure, as seen in the correct answer. Well, I'm using the word correct a lot, answer above. This oxygen can only be to this carbon, the carbon that was add the halogen for this reaction. Again, in this reaction, the oxygen always bonds to the carbon with the halogen, not any of the others. It doesn't happen, period. And when you write a structure like this, that's the same as, oh, draw a hand and you only have 3 fingers. Well, that's not you put the thumb in the middle of the hand. No, it's not there. It's wrong. Well, the same thing here. And that's why if you draw it wrong like this, you get 0 points. And let me give you another example. If I remember correctly, people did. Oh, I didn't realize I was on 2nd page. I got it out quickly this morning. Oops. But anyways, let's go to another example. And the question is, what's the organic product or products? This something similar was on test 2. And the general reaction is this. And the carbon with the hydroxyl will be the carbon with the chlorine. And that's this carbon. And we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. This is the carbon that had the hydroxyl group. Therefore, that's the carbon that will have the chlorine. And there are 4 bonds to carbon. And if you look at the structure I'm drawing, every carbon has 4 bonds to it. Now, what I saw certain students do would be something like this. And that's wrong, because in my eyes and in general and organic chemistry, the way this is written, which is wrong, this chlorine as written is bonded to that carbon. But that carbon now has 5 bonds to it. It can't happen. This carbon, as written, has 3 bonds to it. And it can't happen. And one more example. I think the question was, and I don't remember if I had 1 or 2 carbons here. And here we have an ether plus a halogen or salt, and X can be chlorine, bromine, or iodine. And the general reaction is alkoxide plus alkyl halide. And if you said this is R, which some people did, and this is R prime, then the correct answer is this. But what some people did, and I'll write it in red, this they got right. But here they wrote things like, this is one example, and I'm using names, but I'm trying, and they wrote this. What's that? Nothing. You have a carbon with 3 bonds to it, and you have this chlorine floating around in nowhere land. No, it's got to be bonded like this to a carbon. Now, if you had written it this way and not show the line, I would have given you full credit. But to put it on here, is it bonded to this ring magically? I don't know. And guess what? It's wrong. So that's what I mean by putting the right atoms to the right atoms in your structure. For test 3 and 4 and the final, you're going to have 3 friends you should always use. 1, how many bonds to carbon? 4. There's always 4. I'm going to have to get that fixed. 4 bonds to carbon. That's friend number 1 you should always use. You should check your answers for that. Second of all, do you break carbon-carbon single bonds? No, except for combustion where you burn it with oxygen. That's the only reaction this whole semester where you break carbon-carbon single bonds. Oxygen-carbon or carbon-oxygen, carbon-nitrogen, yeah, you can break those like that, but not carbon-carbon single bonds. And your third friend is when you look at a molecule, look for what's different. Look for what's not carbon, look for what's not hydrogen, and look for what's not a carbon-carbon single bond, because like that, or, ooh, this is broken. I got a place to replace the bat. Like that, that should get your attention because that's where the action is. That's where changes are going to occur, and that's where the fun is. Any questions on that? Because I know you had questions. If that helped clarify, give me a thumbs up. All right, thank you. And if you have any questions, see me after class. But it's a mistake I wanted to point out because on test 3, don't do the same thing. Make sure bonds go to the correct atoms from the correct atoms. All right. It's new chapter time. Oh, wait. It's new chapter time. And I have to warn you, this is a dangerous chapter. Why? Because it's fattening. It's chock full of a lot of calories. And I'll be teaching some really interesting things. It's going to be a real sweet chapter. And what's that? It's carbohydrates. And carbohydrates, what are they? Good question. Let's go to the chapter. Thumbs up, people. Do you see chapter 18 was sections of chapter 15? Thank you. Now, here's a little warning label, not really, caveat from, ooh, fancy word from Dr. White. Now, I'll never ask, but we're going to talk about some biochemistry. And what is that? That's the study of chemical substances found in things that were alive and the chemical interactions of the substances with each other. Now, one of the things I always hear, and it's frustrating, if you follow I don't know if you really call it a zombie idea. It's one of those things that don't change, keep on going like the living dead, a zombie. Dr. Paul Krugman came up with the concept zombie idea. But anyways, not for chemistry, for something else. Functional group chemistry that you've learned for the organic molecules in this class occurred just the same way for bioorganic molecules. They're just more complex looking. In other words, the functional group chemistry going on in your body is the same as what we studied. There's no magic, there's no bookie going on. It's just complex structures, but it's the same functional groups. Alcohols react like alcohols, ketones react like ketones, double bonds, etc. And by the way, a biological substance is a substance found in something that was alive or is alive, like plants and animals, including us. All right. Oh, hold on one second. I forgot to turn something off. There we go. All right, let's get into this chapter and let's talk about carbohydrates. You should know what a carbohydrate is. And that's the definition. What is a carbohydrate? It's a polyhydroxyl aldehyde or aldehydes, polyhydroxy ketones, or compounds that yield such compounds upon hydrolysis. What that means is you take a compound, react with acid and water, you'll get either a polyhydroxyaldehyde or polyhydroxy ketone. What the heck is a polyhydroxyaldehyde or polyhydroxy ketone? Well, let's take a look at the word polyhydroxy. Poly means many. Hydroxyl, and sometimes I say hydroxy, my mouth gets lazy, is something with a OH on it. So, and aldehyde, you know what that is, and ketone, you know what that is. Now, one thing I should mention in my software and also carbohydrate chemists don't draw an aldehyde this way. They draw it this way. And you have aldehyde. And so you should know what is a carbohydrate. If I ask on test 3 points each or 3 points, what is a carbohydrate? It's a polyhydroxyaldehyde, polyhydroxy ketone, or compound that yields such upon hydrolysis. Now, listen carefully. I am not going to ask you to learn the structures of any carbohydrates. You'll see on my test and also the problem set, I've made it easier for you. But I will teach you those structures. And this one right here is glucose. And glucose is the common name for this polyhydroxyl aldehyde. Right up here, I have an aldehyde. And notice 1, 2, 3, 4, 5, and that's 5 hydroxyl groups. Now, this is called the Fischer projection, named after the great German chemist Emil Fischer. Yep, he's the same one who discovered how to make esters, but he's most known for his work with carbohydrates, and I'll teach you what the word sugar means, smaller sugars, and he elucidated, that means figured out what the structures of the various small sugars are. Unfortunately, it also killed him. And I'll talk about that sad part too. And this is called the Fischer projection. And every intersectional line here is a carbon. And later in this chapter, I'll teach you how that shows stereochemistry. And I'll also teach you what stereochemistry is. So this has a lot of hydroxyl groups on carbon, has an aldehyde. This is a carbohydrate. Now you're used to hearing the term carbohydrate, or more likely carbs. And what they're really talking about are starches. And I'll teach you later on this chapter that starches are also carbohydrates. But in a chemical definition, glucose is a carbohydrate. Now, another carbohydrate is fructose right here. And you do not ever have to know the structure of fructose. I'll never ask on a test, draw fructose or glucose or what's the name of these structures. Now, if we look here, there's a carbon right here. We just don't show it. If I have a carbon here and a carbon here, what do I have in fructose? A ketone. And therefore, fructose has a ketone, as, a hydroxyl group. No, 2, no, 3, 4, 5, and that's a lot, and I'll call that polyhydroxyl ketone, and that's why fructose is a carbohydrate. And we'll talk more about fructose and glucose this chapter. All right, now, when we talk about carbohydrates, I'm going to turn the switch off. Will this be on a test? Click. And there's certain words that are used, and I just thought I'd just run by those. A monosaccharide, again, this will never be on a test, is a carbohydrate that contains a single polyhydroxyl aldehyde or ketone. Therefore, glucose and fructose, which I'll never ask, are monosaccharides. Mono means one, saccharides means small. I don't know what it means. It's used by, let's find out. I never thought about it. And it's another term for sugar. Okay. And I'll teach you later on, maybe today, what's a sugar. So I've learned something new today. Now you see how a PhD should operate. When you're not sure of something, you find out. All right, now, monosaccharides, single sugars, are carbohydrates that contain a single polyhydroxy aldehyde or ketone. Now, I should mention up front, I am not a carbohydrate chemist. Even though I do carbohydrate chemistry, I like carbs, potato chips, French fries, pizza. Uh-oh, I just gained weight. But anyways, I've never really done anything in the lab with. I tried it once in one company. I had an idea. Are you ready for a funny story? I think I mentioned that chemical companies have what's called a sample room. And if you're in a reputable company and you think, oh, let me try, I think this product this company makes might be useful in my research to make a new product that my company can make. And I'm going to call that company up and say, can I have a sample to test an idea of mine? Well, I had an idea with fructose, and normally they send you 4 ounces, maybe 16 or a quart. If you really need it, under special circumstances, I'll send you a 5-gallon pail. That's a lot for doing research in a research lab. It's a lot of chemical. But anyway, so I called up corn products company, CPC. I don't know what they're called this year, but anyways, they used to be CPC, and I was working for a very large international company, Borden Chemical, which is now Hexion. And I said, yeah, I have an idea. I talked to a salesman to use fructose your company makes. It's called high fructose corn syrup. Can you send me a sample? And he said, sure. He was all excited. Do you think? I said, oh, if it works, could be good business for you, but it's a really wild idea. I don't know if it'll work or not. It didn't, but you try things like that because some of my wild ideas do work quite lucratively. So I got all excited and told the sample room, and they sent me five 5-gallon containers of high fructose corn syrup. Unfortunately, there are two types of chemicals you can get from chemical companies. One is industrial chemicals, which and the other is food grade chemicals. You never want to eat industrial chemicals, even if it's a safe chemical, because it's not biologically it might have certain germs, microbes, whatever. Now I'm going to be very technical, ickies that will get you sick in it, where food grade is going to be safe to put in food products. Well, he sent me industrial, and now I only needed about 100, maybe worst case scenario, 1 pound. And now I've got 5-gallon, so that's, let's see, each gallon is 8, that's 40. That's 200 pounds of high fructose corn syrup that most of it I had to get rid of. The lab manager who was in charge of waste products was quite upset with me because why'd you guess? I didn't ask for that. I tried calling, oh, we can't take it back. And anyways, but I thought I'd tell my cute little story about that I don't do carbohydrate chemistry other than what I eat. Now, another term which I will not ask switches off is oligosaccharide. I don't even know if I'm pronouncing it right because I'm not a carbohydrate chemist, but that's a carbohydrate that contains from 2 to 10 monosaccharide units bonded together. And I'll be teaching you how they can bond together this chapter. Now, switches on. There's one special oligosaccharide you should know, and that's a disaccharide. And I think you remember, I hope you do, in organic chemistry and chemistry in general, di means 2. And this is a carbohydrate that contains 2 monosaccharides that are covalently bonded together. And the most common disaccharide that you should know is sucrose. And sucrose, which is a common name, not an IUPAC name. I don't even know what the IUPAC name is for table sugar, but I'll show you the structure later on. That's the stuff you buy in the 4-pound bags. Now it used to be 5, but to charge us more, they cut back a whole pound, even though they kept the price same. They've dropped the amount they give you by 20%. But anyways, no, 25%. No, 20%. But anyways, sucrose is table sugar. You should know what is sucrose, it's table sugar. What's table sugar? Sucrose. That's the white stuff you put in your tea like me, or coffee, or when you're cooking, you put in things to make things sweeter. Now, switches off again. There's a last designation called polysaccharides. Poly, as you've learned, means many. Saccharide is sugar, many sugars together. Those are carbohydrates made up of many monosaccharide units, and we normally have a name for this, and it's called starches. And we'll talk more about starches later this chapter. Now, it's time to jump back to chapter 5. If you were reading a book, this is where I differ from the author. I'm not going to teach something until you need it. Don't follow. I'm one of those instructors who, just because the author of a book says 1, 2, 3, 4, 5, doesn't mean always, if you know how to teach, that it's the best order. And, excuse me, for this class, I have decided long ago when I started teaching, now is the time to teach stuff in chapter 5. So let's get into that. And it's part of the important aspect of carbohydrates. Now, this chapter in this area talks about chirality. Now, there's a concept called handedness, and carbohydrates exist in two forms like your hands. There's a left and a right. Now, where does this word chirality come from? Well, someone decided, let's use the Greek word for handedness, which is chiral. And you should know let me spell it right. That chiral is Greek for handedness. And a couple of, I think it was 3 summers ago in a Chem 170 class, I actually had 2 people who spoke Greek. And I asked them, is this true? Because I read it in books and everything. They said, yeah, it is. And so it is Greek for handedness. And we talk about chiral, or using an adjective, chirality. Uh-oh, I'm getting fancy English on you. So you should know chiral means handedness. It's Greek for handedness. So when we talk about handedness, I have to talk about mirror images. Now, at this point, I'm going to assume each one of you at one time in your life up to now has looked into a mirror. You know, like if you look in, like when I'm trimming my beard, I'm doing it in front of a mirror, and you can see your reflection. And there are 2 types of mirror images, what most people call the reflection you see in the mirror, chemists call mirror images. And what are those 2 types? And by the way, the switch is on full blast right now. You should know this, what I'll be talking about. Now, there are 2 types of mirror images. One is superimposable, and the other is non-superimposable. What do we mean by that? Well, superimposable image is an image that coincides at all points when the actual item or whatever in front of the mirror and the image are laid on top of each other or over each other or upon each other. Hold on, I just forgot to get something. I'll be right back. Now, again, superimposable image is an image and its mirror image that coincide, 2 types of mirror images. It's the image that coincides at all points when images are laid upon each other. Let's take a look. Let me turn on my camera. All right, can everybody see this? Notice I have, this is a carbon atom, center carbon, but just think of a center. Notice it has 2 silver spokes, they're carbon hydrogens at the end if this was methane, and 2 black ones. And oh look, I've got another one. And if there were a mirror right between us, they're mirror images. See how this reflects into this, the blacks reflect. Now, if I go like this, notice how the silvers line up. If I could push them together, they'd line up point by point. The black and black would line up. So these are mirror images and they're superimposable. So this is if this were the item I put in front of the mirror, I would see this reflection. And I'm going to have a homework assignment for you in a little while. Now that's superimposable. The other type is non-superimposable. And that's an image where not all points coincide when the images are laid upon each other. Non-superimposable. And I have a homework assignment for you. I'm going to assume everybody has access to at least one mirror. Stand in front of the mirror and hold up your left hand. Pretend I don't have my ring on. And what are you going to see in the mirror? This, the reflection, and it's your right hand. Now, your right hand are mirror images, but they're not superimposable. Notice if I line up my thumb, the other fingers don't line up. If I line up my middle finger right here, the others don't, like my pinkies don't. Everybody know what a pinky is? They still use that term, pinky? Remember pinkies swear or whatever? All right, so your hands are mirror images, and the homework assignment I have for you is go to a mirror, hold up your left hand, or you can do your right hand, and what you'll see in the mirror is your other hand. I bet you didn't know they were non-superimposable, and they aren't. And that's why we use the term chiral, meaning handedness, because molecules are like that. Oh, important story I should tell you. This is funny as heck. Students were having a lot of trouble with this the first couple of times I used the slide when I started teaching, until one student raised his hand and said, you know, you don't have the word superimposable or non-superimposable on there. Remember, I always say I'm first one down in the spelling bee. I said, oh, what do I have? You have superimpossible, non-superimpossible. No wonder the students were having trouble. It was impossible. Well, it's not, it's imposable. So you have two different types of mirror images. Superimposable, that's where the images coincide. You can push them together and they line up. And then we have a non-superimposable mirror image, like your right and left hand, where the images do not coincide with each other. Now, why do we need that? For this. When we talk about the term chirality in chemistry or just in general, there are two types of definitions, and I've just turned the switch up to 100 for this slide. Quick, get my stylus. And the first one is, when we talk about chirality, there's what's called a chiral object. And what's a chiral object? That is an object that is not identical to its mirror image. Another way of saying that is a chiral object has a non-superimposable mirror image. Again, chiral object, non-superimposable mirror image. The other type of objects in chemistry and also in life are achiral. Now, the prefix A means without. I once worked with someone who was not immoral. That person was amoral, dangerous person at times, because they had no moral compass whatsoever. And he wasn't a mean or anything like that. He just had no moral compass. You have to be careful around him at times because he'd do some wild things. I won't get into that, but very nice person, but he was amoral. But achiral means a without chirality, handedness. So an achiral object is an object that's identical to its mirror image. And that's achiral object has a superimposable mirror image. So we have two types of objects: chiral object, non-superimposable mirror image; achiral object, superimposable mirror image. Again, chiral object, non-superimposable mirror image; achiral, superimposable mirror image. Now, are your hands chiral or achiral? Let's do it this way. I'll make it even simpler. Is your left hand chiral, or your left hand? Oh my God, I'm looking at the screen and going, well, never mind. But anyways, is your left hand chiral or achiral? Well, if you don't know, here's the hand, here's the mirror image. Oh no, it's not superimposable. So my left hand is a chiral object. My right hand, same thing, it has a non-superimposable mirror image. And my right hand is also chiral. By the way, if somebody assigns the name right or left to it, that's immediate hint. It's chiral because it's got handedness left or right. Now, I could ask the question, is your face chiral? How many of you have ever played Simon Says when you were a little kid? Raise your thumb, do a thumbs up. Did you ever play that game? Let's see, a couple. Okay, some of you have. And I'm going to play Dr. White Says. Dr. White says, touch your right cheek with your finger. Could you do that? And by the way, now I'll say Dr. White says you can take it off your right side. Well, if you can touch your right from your left, that means your face is chiral. I bet you didn't know that. Now you can impress your friends, neighbors, and loved ones with that. Oh, by the way, I can't resist. Everybody know what that is? It's a spider doing push-ups on a mirror. Couldn't resist. I do that every time when we talk about chirality. All right, but now I have to warn you about something very important and serious. Next hour or two, or maybe a little longer, I'm going to be doing some artwork. Please don't laugh so hard you fall off your chair, bust a rib. Don't, but be careful. It's going to be funny because I have no artistic talent whatsoever. Zero. My mother was a very good amateur artist. Not one iota of that ever rubbed off on me. None. But anyways, let's look at some things in our daily life. Excuse me. Remember, chiral, object with a non-superimposable mirror image. Achiral, object with a superimposable mirror image. All right, since we're near the break, I'll do two now, and we'll do some more afterward. And the question is, are the following chiral or achiral? 3 points each. Well, how do you do that? We have to determine, does something have a superimposable or non-superimposable mirror image? So what I like to do is think about the object. So let's do the sewing needle, and don't laugh too hard. Here I have a sewing needle, place to put the thread and the sharp pointy. And if I had a mirror, and this is my mirror, you don't have to do this, but it helps me and I do it. Here's my mirror image. If I drew it correctly, this one is superimposable on that. Therefore, a sewing needle has a superimposable mirror image, and that makes it achiral. A means without chirality or has a superimposable mirror image. Now, let's look at B, your left foot. Well, as soon as you see the word left or right, you can immediately say it's got handedness. It's chiral. But if you don't believe me, when you have a chance, go to a mirror and put your left foot in front of the mirror, and guess what you'll see? Your right foot. And if you have a chance, take your right foot without your shoes or socks on and put it over your left foot. And just like my hands are not superimposable, your big toes will line up, but the rest of them don't. Or your little toe will line up, but not the rest of them. Your feet are non-superimposable mirror image. That's why you have a left or right. And let's wait until break. And now it's time for a break, give or take 30 seconds. So let's take a 5-minute break, and I'll see you in 5 minutes. Come back at 1:55. Welcome back. All right, before we go on with chirality and the example, I just remembered I forgot to do a couple of things. I call them public service things. And I really should have done it in the chapter with fats and oils. Now, when I moved in this house a long time ago, and I was moved in, within about 2 weeks or so, the sink in my kitchen stopped up. And I don't think I told this story. If I did, somebody give me a thumbs up or say you've already told the story. But anyways, so what do? I called the Roto-Rooter guy. And the Roto-Rooter guy came out and did his thing, and the sink was open. And within a couple of days, it stopped up again. I had a guarantee, 6 months, I think. Called him up and said it stopped up. Oh, he apologized, came out, did it again. And within a week, it stopped up again. I'm not putting any grease or any garbage down there. It's just water, soap and water, whatever, when I clean my dishes. Because I'm alone, I don't use my dishwasher. It doesn't make sense. So he comes out again, does his thing, and within a week or two, it does it. Now I'm upset, not because of the money I paid him. That's immaterial. By the way, I was making big bucks then. And so it was the time I was wasting having to wait for him to show up. And when he did show up, we came the third time. He said, well, I'll do that, but I'm going to pour this down. That will help. I said, I look at the bottle and the label. I looked at it, and it had some surfactant, soap, and some other stuff that really I don't think would do the job. And he put it down there, and guess what? It was starting to clog up again. So I figured, heck with him. He was trying to do his job, but it just wasn't getting done, excuse me. And so I went to my local Home Depot. I don't get any kickbacks from them. And they have a big wall of drain cleaners. And I'm looking at all of them, and a nice gentleman who works there comes up to me and says, can I help you? And I said, sure. And I say, all those on there, which one did the plumbers use? And immediately, like that, he points to this one. And I picked up that one and looked at the label. I looked at some of the others. And being a chemist, and really an organic chemist, but a chemist would know this, I saw the difference. And that compound, that drain cleaner, had sodium and potassium hydroxide, a base. All the others on there, like Drano and all those, had hydrochloric acid or sulfuric acid and acid. I looked at, oh, it's got a base. He said, no, that's an acid. I said, look, I got a PhD in organic chemistry. That's a base. He said, no, it's an acid. And at that point, I learned a valuable lesson. Never argue chemistry with someone who works at a big box store. It's not worth it. Just I thanked him, and the stuff worked. And I've used it since then once other time, and a number of my students have used it. My brother-in-law had problems. It also works in the bathroom with hair in clogged sinks or bathtubs, and my students have used that. What's this product? I think I might have told the story, but I should do it again. Everybody see on your screen the black bottles that say Instant Power Hair and Grease Drain Cleaner? This stuff works like a charm. The other stuff I wouldn't use, and I'll explain why later, but I keep this size bottle in my house for emergencies. In the last year, after a number in one sink, after 20 years, it finally said, you should clean me out. And I did. And boom, it was clean like it was brand new. And after about 12, 13 years, my kitchen sink clogged up again, and I used it. And I keep it in the house for emergencies. Now, this is the only one of the whole wall that it's in a thick Ziploc bag. And on the bag, it says, please use proper uh, proper eye protection. Now, how does this work? And again, This is not going to be ever on a test, but I showed you soap the other day is made up of long chain carboxylate anions. Now, in your water from the city or wherever you live, you have calcium plus 2 ions. And what happens is you form this calcium carboxylate anion. And why is there 2? Because all molecules have a net zero charge. This is a -1, this is a +2, so I need 2 of them, so this equals 0. Well, this is twice as heavy, and if you remember the lab, we did this precipitates out, and this is your bathtub scum. Well, wrong, I got my stories mixed up. I'm thinking wrong story, and I was going to do it afterward. Let's do this. You shouldn't, but, and I'm sure the previous owner did. If you put grease, like bacon grease or whatever, down the sink, your fat will solidify and clog up. And what are these esters? And you learn from the fats and oils, if you react this with sodium hydroxide and water, you get the alcohol plus the carboxylic acid, but in this case with base plus the carboxylate anion you would have used to make that. And what it does is it breaks down this big thick thing to things that are more likely water soluble and smaller. And that's how. Now acid will do the same thing. Well, actually not that way. Acid and water will break it down, but the reaction is much slower. And if you have an older house like mine, from in your utility room somewhere, you have cast iron pipe that goes out of your house to the pipes that go to, which are usually clay, if you're old like mine, to the city sewer line. And acid will react with cast iron, base will not. So there are 2 reasons why you use that. So you should use, when you have clogged pipes, either hair or grease. Now hair is an amide and base saponification of an amide, I've already taught you, and that's how it breaks down to hair. And this is the best, and I've had numerous students and family and friends of mine use it, and we all love it. And I don't know why it doesn't have 5 stars. Somebody who is inept used it, but that's good. Now, the other thing I think I talked about, but I'll do it again real quick because I already wrote this up here, is bathtub scum comes from R sub T is tallow, C18 with and without a double bond. And if you have calcium salts in your water, this is your soap. Oops, wrong thing. You'll get this, and this is your bathtub scum. Or shower salt too. That's the best way to describe it. And when I got tired spending a lot of time, because of all the things I hate the worst is cleaning a bathtub out. And I let it go until I have to do it, and it makes it even worse. So I challenged myself a couple number of years ago. You're an organic chemist. how do you get rid of this stuff down the drain quicker? I said, well, if you use an acid, but certain acids I wouldn't use in my house, but if you use an acid, this is an acid, you'll break this down to smaller molecular weight. These two things, and this is going to be now more water miscible or soluble. Well, it turned out I did a little research. You could use vinegar, but you can't buy strong vinegar or strong acetic acid, and vinegar is only 4%. Stronger stuff, well, you don't want your house smelling like vinegar, and it's dangerous to use at home. What's something safe? And what I did was look around. And I found my brother-in-law had been using this product, my sister, on their stainless steel. And it's called Barkeeper's Friend. And you can get it just about anywhere. My supermarkets around here have it. Walmart, Target have it. Like I said, just about anywhere. And what makes it interesting? If you look here, it has a solid to help soap. That's what linear stodecyl sodium sulfate is. And it has oxalic acid. What's oxalic acid, you say? Here's the structure of oxalic acid. It's a simple dicarboxylic acid, and it's in about 8% in Barkeeper's Friend. And now for the acid, use this. And you react this with this, and what you get is the carboxylic acid, fatty acid, which is now more water soluble, and you get this carboxylate anion. Because oxalic acid has 2, but it's still a low molecular weight. And that's how you do it. So what do you do? Well, I got to do it this weekend. Even with this, I put it off. I don't like doing it. But anyways, I have a shower stall, and the shower head is removable. Turn it to hot water, spray the walls, and works on the walls too. The bathtub, get it nice and hot and wet, and then take the oxalic acid, sprinkle it on there. It's a powder. They have a liquid gel, but I've never bought it. Someday I will, but I haven't. And you take paper towels, sponges get fouled up too easy, moisten it and make a paste all over it. Let it sit for about 10 minutes and come back with paper towels. If you've got a real bad area, the green Scotch-Brite pads, cut them in half so they're smaller ones, and you just scrub it a little. That's all you got to do, and rinse it down with the shower head. And I can do a bathtub now, mine, even though I still hate doing it, I got to do it. My actual work time where I got to actually be doing anything is only about 5 or 6 minutes. And it's within 20 minutes, because I wait 10 minutes, it's done. And that's how you do it. I thought I'd teach you that. All right, we were talking about, are the following chiral or achiral? Let's have some fun. And let's do, are the following and why don't you try these four? Are the following chiral or achiral? Chiral, non-superimposable mirror image, achiral, superimposable mirror image. And let me do one more. This is fun. Oops, wrong. And the last one I just added was a round rubber ball. And the reason I was thinking of that, there's a famous song none of you have never heard, but I bet it's on YouTube. Like a round rubber, you come bouncing back like a round rubber ball. And for those of you who haven't looked at it, you should check out my list of songs and other great things on D2L. There's a, on the left side, a place you can click to download the files. And that reminds me of an old favorite by Nervous Norvis, and that's The Wild Dogs of Kentucky. That was a big hit when I was in 3rd or 4th grade. I think that was my first record my parents ever got for me. And the flip side was Ape Called Doubliaba. Remember, you're trying to figure out, are these on the list chiral or achiral? And those who finish early, I try and give everybody time to do it. So hang in there. And also, I just remembered on Monday, I will go through test number 1 answers. And I will also go through the carbohydrate, and not the carbohydrates, the fats and oils or the lipids problem set on Monday. All right, anybody else need more time? All right, let's do this. We're trying to find out if the following items are chiral or achiral. And what's a chiral object? Something with a non-superimposable mirror image. Well, as soon as you see the word right or left, you know immediately it's chiral. But in case you weren't, all right, warning, warning, awful art time. Wow, that's one of my best ones ever. And this is a glove. And don't forget, it's got a palm. If this is the back end, it's different from the palm, and it would be a non-superimposable mirror image. Now, next one, a tube sock, and men's tube socks don't have toes. Some women's do, so this is one without toes. And let's take a look. Like I said, here's my sock. Here's my mirror image, sort of, and you'd find out they're superimposable. And also you can put them on either foot. So that means they're achiral. Uh-oh, this is dangerous, a four-door car. Let's take a look at this. I'm going to make some more room down here. Headlights, steering wheel, wheels, rear lights, tailpipe, door, 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 door. And if I do the mirror image, wheel, door, door, wheel. Now here I'll have my headlight, steering wheel, headlight, wheel, door, door, wheel. And here I have this, my tailpipe over here, my other brake light there. Now, don't forget this has a roof on top, and underneath are the wheels. This is non-superimposable. You say, well, I can flip it over. No, so you flip it over, this would have the wheels on the bottom, and when you flip this one over, the wheels would be on the top. So it'd be non-superimposable. Therefore, a car, four-door, or even two-door, or a bus is chiral. And if I were standing in front of the car, I said, go ahead, get in on the left side, you'd know which side I was talking about. That proves it's chiral. Now, one thing I should talk about, do I have time? Yeah, I have time. Notice here the steering wheel is on the opposite side. When I used to go to England, especially, I spent a lot of time in Manchester and also sometime in Liverpool, but mostly Manchester. A few times in London. It was dangerous because twice I almost got killed crossing the street. Both times policemen, bobbies, saved my life, literally. They grabbed me, what the heck are you doing, sir? And they said, you're American. I said, yeah. I said, see that on the street? It tells you, and they had letters on the busy streets, look the other way for oncoming, because we're used to traffic coming this way when you're walking. No, it's coming this way. So I finally figured out a safe way for me to cross streets in England. And that is when I was going to cross the street, I'd find a little old lady or man. And when they stepped out, I figured it's safe because they'd get smashed first. That's sort of gruesome, but true. Thank God I never had to drive there. The first time I was in England, I was in a car in the front seat with a colleague driving who was English. And we come to a stop sign, and I go like this, like I'm thinking I'm driving. My brain said, you're in the driver's seat, stop. And my colleague broke out laughing, said, American, yep. But anyways, that's my English story. It's dangerous crossing the streets in England. Nice place, but dangerous. All right, so that's chiral and achiral. And this is a skill you should have. Hint, and this is the wrong slide. All right, now, in real life, we talk about molecules, and molecules have what's known as chiral centers. I'll never ask the definition of a chiral center. But that's an atom in a molecule, and for this class, it's going to be a carbon atom that has 4 different groups or atoms, and I should have added atoms that are technically the groups that are tetrahedrally bonded to it. And tetrahedral is this type of structure, which methane has. And let me talk about it and show you what you need to know how to do. All right, does everybody see on the whiteboard, circle the chiral carbons in? Thank you. All right, so 3 points each. Circle the chiral carbons in the following molecule. I could have written that too. Let's look at A. I'll do this. So what is a chiral carbon? It's a carbon that has 4 different atoms or 4 different groups or a combination of 4 different things attached to it. Well, there's a quick way to rule out carbons that are not chiral. If a carbon has 2 or more of the same atom or group on it, it can't be chiral. And therefore, I can say, oh, look, 3 hydrogens, that's out. 2 hydrogens, that's out. 3 hydrogens, that's out. And they cannot be chiral carbons because they have to have 4 different atoms or 4 different groups. If a carbon is in a double or triple bond, whether the carbon or oxygen or nitrogen even, it can't be chiral. So immediately, this is out and this is out. So these are out. And what do we have left? This one and this one. Let's take a look at this one. It has a methyl group. It has this whole thing attached to it, has a hydrogen, has a hydroxyl. That's 4 different things. And therefore, let me get another color. I haven't used green. I'm going to circle that one. It's chiral. And if we look at this carbon, it has the same thing, hydrogen, bromine, 2, a methyl group, and this whole thing I'll call R, 4 different things. That's chiral. So there are only 2 chiral carbons in there. And that's how you do circle the chiral carbons, 3 points each. And why don't you try this one? Circle the chiral carbons, 3 points each, or 3 points for B total, not per chiral carbon. Now this is a rule of thumb, not a true thing, always true, but there are a few exceptions, and I'll never put those on a test. Just look at the structure. I did one that's a little sneaky, but it's good practice. All right, let's do this. Now, if a carbon has two or more of the same thing, it's out. So this has 3 hydrogens, it's out. This has 3 hydrogens, it's out. This has 2 hydrogens, it's out. This has 2 hydrogens, it's out. Now, if I look at this carbon right here, it's in a double bond to oxygen. So anytime you see a carbon in a double bond, it's oxygen. Now, this carbon right here is a little sneaky, and I shouldn't have really done this, but I did. So notice it has 2 methyl groups. So that means 2 of the same group, it's out. And that means we only have 2 things to contend with. These 2 carbons has that thiol group, SH, hydrogen, this whole thing, and this whole thing has 4 different groups. And this has a chlorine, this carbon, a hydrogen, this aldehyde, and this whole thing. And that's, let's call it R, and let's call this R prime. So you have hydrogen, chlorine, R, and R prime, 4 different. So those would be the 2 you circle. Oh, let's do one more. Actually, let's do more than one. Oh, I've got to, hold on. I've got to shut this down. Give me a minute. I missed that. Sorry about that. I still haven't figured out why it does it. Something going on that I have so many things opened up, my computer gets overloaded and says, time out. All right, circle the chiral carbon in this molecule. I don't know what letter I was at, D, let's call it.
You can't see the whiteboard.
Oh no. Thank you, whoever let me know. All right, can you see it now?
Yes.
Thank you, Natalie. All right, when you're done, give me a thumbs up. Well, half of you are done. All right, let's do it. Now, students hate rings. Dr. White, Mother Nature loves rings. How many bonds to carbon are there? 4. So if we look at this ring, we don't show it, but there are 2 hydrogens there, 2 there, 2 there, and 2 there. And because of that, this is out, this is out, this is out, this is out. So when you have 2 or more of the same atom or group or combination thereof, you don't have a chiral carbon. Now this one has a hydrogen and this one has. And I could say this carbon right here has a hydrogen methyl, this part of the ring, and then this part of the ring, which would be different. So that would be a chiral carbon. If I look at this carbon, I can say the same thing. Hydrox group, hydrogen, this part of the ring, and this part of the ring, which are all, this is different from this, different from hydroxyl, different from hydrogen. Therefore, this is, and let me clean this up again. And these would be chiral. Now, let's look at the following. I'll do one, then I'll let you try one. Have to think for a while. That's right. Now, you don't have to know the structure, but this is glucose, the most abundant sugar in all of nature. But anyways, circle the chiral carbons. Well, if we look at this carbon right here, it has 2 hydrogens, so that's how. This carbon is really this, an aldehyde. Therefore, this is out. But this carbon has 4 different groups, aldehyde in the bottom chain, hydroxyl, hydrogen. Same thing here, same thing here when I put the hydrogen there, and it should be there, and same thing here. And glucose has 1, 2, 3, 4 chiral carbons. And let's have you try one. I'm going to make one up. So I don't even know if this exists in nature, but it exists in my whiteboard, so I can write it. And this molecule circle the chiral carbons. I see one person's done. Thank you for letting me know. And then there was 2. All right, let's do this. Now, let's look at this carbon. Remember, it's an aldehyde. And if you have a carbon in a double bond, whether it's oxygen or anything else, it can't be chiral. And I have this carbon has, when you have 2 or more of the same group, 2 hydrogens, example, it can't be chiral. Oh, but look here. This carbon has 2 hydrogens. It can't be chiral. Now, what do we have left? This one can, hydrogen hydroxyaldehyde, and the rest of this chain. And turns out you can draw a similar for that and this one. So this molecule has 1, 2, 3 chiral carbons. And that's how you do circle the chiral carbons. That's a skill you should have. Now, switches off for this slide in the sense I'll never ask you about it, but there's something called stereoisomerism. Say that 5 times quickly. No, you don't have to. And that's isomers. Isomers are molecules that have the same number and same type of atoms, but they're connected differently. And stereoisomers are isomers that have the same molecular and structural formulas, but differ in their orientation of atoms in space. And isomers whose atoms are connected the same way, but differ in their arrangement in space. And in order to have, and switches off for the slide, to have stereoisomers, you must have a chiral center for this class, it's carbon, and it must be structurally rigid. What does that mean? Now, if you look at a quaternary ammonium salt, the nitrogen can have 4 different groups, but with a carbon, it's fixed. With a nitrogen, it can flop like this. How many of you have ever been in a heavy, windy rainstorm with your umbrella, and all of a sudden the wind makes it go pop, and you can pull it back down if you haven't destroyed it, the wind didn't destroy it. And I've been able to do that, and so you don't get wet, and maybe again it'll go pop, and then you'll pull it back down. Well, nitrogen can do the same thing with the bonds to 4 different groups, which is why, yeah. But in this class, I'm just going to stick to carbon. And it's show and tell time again. Notice I have the models again, but now I have red and yellow on this one, plus the black rod and the silver rod. And notice they're, oh, what did I do wrong? Hold on. Let me get it oriented right. They're mirror images. Red goes to red, yellow, yellow, silver, silver, and far away black. And they're non-superimposable. When I go like this, silver, silver line up, the centers line up black to black, but oh no, the red and yellow are not lining up. Well, flip it, Dr. White. Okay. Well, now the red and yellow line up. But if we look here, one has silver up, the other black. This has silver, black back, and this, so they're not lining up. So these are mirror images. They're chiral, each one. This is a chiral carbon, silver, black, yellow, red. Now, why did I bring that out? Well, you'll see in a second, maybe a little farther, but let's continue on. Now, a special type of stereoisomer is an enantiomer, and the switch is on full blast now. What is an enantiomer? I'll never ask you what's the definition of an enantiomer, but you should know how to identify enantiomers or draw them. And what is enantiomers? They're molecules with non-superimposable mirror images of each other. And here is glucose. And let me go to the whiteboard. All right, let's get some space. And if I were to ask you, and by the way, this is glucose, you don't have to know the structure, but I'll use the name because I know it. If I ask draw the enantiomer this, what I'm really asking is draw the mirror image. Now, what I found for me that works, I put my mirror in, it's a mnemonic device. I have my backbone. Now, achiral carbons, you don't have to worry about the mirror image. So I can draw it this way. Or if you really want, and some students want to, you could have drawn the mirror image, but it doesn't matter, like this. Either way is okay. But if we look at this carbon right here, what's closest to the mirror, hydroxyl group, you'll see first in the mirror. What's farthest away, hydrogen. This one, closest hydrogen, farthest hydroxyl group. Here, what's close to the mirror, hydroxyl group, you'll see that first and farthest away is the hydrogen. And here, close to the mirror, hydroxyl group, farthest away, hydrogen. Now, this is a carbonyl carbon. It's achiral, so I can just go like this. If you wanted to draw it like this, that's okay, but either way works for me. And this is the enantiomer, and that's how you do it. What I'm really asking you to do is draw the mirror image. And if I look at the clock, it's time to take a break, and I'll come back and we'll practice a couple more of these. So let's take a 5-minute break. I'll see you at 2:51. Actually, I went a whole minute. 2:51. Let's take a 5-minute break. I'll see you at 2:51. Don't be late. Models. Let's get started. Ooh, I'm on time too. All right, let's go back to what we were practicing, and that is draw the enantiomer of the following. And what's an enantiomer? The mirror image. So what I'm really asking you is draw the mirror image of the compound I put down there. So let's have you try one. Now, one thing I'll teach you about Fischer projections, like the car, these show stereochemistry. I'll teach you that in a little while, and you can't flip them over. So that's why they're non-superimposable, and they are mirror images. So why don't you try the following? I should warn you, the closer to August it becomes, the worse my hydrogens are. No, that's just a joke. And the question is, draw the enantiomer of that molecule, 3 points each. Your turn. Oh no, the hydrogens are disappearing. Remember, that means draw the mirror image. Well, I see one thumbs up, but I'll be patient and hopefully you will be too. Oh, and then there was 2. All right, let's do it. The question is, come on, draw the enantiomer of, and you were given B. What do? You draw the mirror image. Now, you don't have to, but I like putting in my mirror. It's some mnemonic device or device that helps me. And I'm going to have my backbone. I'm not going to lose my carbons. This is achiral, so I can immediately draw it like this. This is achiral. And what's close to the mirror here, I'll see in the reflection. If you don't believe me, go put your right hand or left hand in front of the mirror, and your palm is closest to the mirror. You'll see the reflection of your palm in the mirror. If you turn your hand over, it'll be the backside is closest. And what's close to the mirror here, hydroxyl. I'll see that first, farthest away, hydrogen. Ooh, hydrogen is closest, farthest away, hydroxyl. And same thing here. And these are enantiomers. This is the enantiomer of this. By the way, your hands are enantiomers too. Non-superimposable mirror. Well, it's for molecules, so I take that back. Switches off for this. There are other types of isomers. One is called the diastereomer, And those are stereoisomers whose mirror molecules are not mirror images. An example of that would be a molecule with a cis or a trans. One has cis, the other has a trans double bond, like the 2-butene cis and trans I gave when I first taught you cis and trans. Now, switches off for this, and I just thought I'd show you about a Fischer projection. Now, Fischer projection is, example would be, and I'm going to show you with my model, if you take the three-dimensional, and rotate it to the right and flatten it out, you get this. And this carbon is this carbon. But this is showing this because these two carbons, or C and E, are coming out towards you. These two are going back. And let me show you again, switch is totally off. I used to put this on a test, and guess what? Students always got this wrong. And I said, there are more important things I'd rather show. But still, if you take other classes, and if this were a molecule, and I'm going to do the Fischer projection, I'd flatten this out, and these would be flattened out. And on here, I'd see Y, this side R, red, on top here coming up black, and down here silver. But it's really showing these two are coming towards you, and these two are going away from you. And that's how you do a Fischer projection. Won't be on test, but now you understand when you see those intersections of the line, it's really each carbon looks like this. And that was one of the great things Emil Fischer did to help, fancy word time, looking around to see if anybody's watching. What am I doing that for? Elucidation means to figure out what the structure is. He elucidated the structure of small sugars, which was a great advancement. Now, next couple of slides, I'm going to skip right now. We'll come back to next week. So I want to get to something more important that I want to cover now that you can look at over the weekend. All right, quick thing, switches off. Hold on, let me get this a little smaller. Right here, switch is totally off. So I'm going to zoom through this. Carbohydrate chemists call something called aldose aldoses. And those are monosaccharides that contain an aldehyde, which this is one. Glucose is an aldose. Now they have ketoses, and those are monosaccharides that contain a, oh, I forgot, thought I shut this off. Hold on one sec. Oh, I missed these, or it came back on me. That's better. It's a molecule that contains a ketone. Where's the ketone? Remember, here's a carbon, there's a carbon here. So the carbonyl to R and R prime ketone. And a monosaccharide with a ketone is called a ketose. How many of you ever heard of the problem called ketosis? And that's something that people are diabetic have to worry about. That, what was it? 4 summers ago, it was unusual. It was 3 or 4 summers ago. I had not one, but 2 students who are diabetic. And when I teach face-to-face, one of the things I do is I ask all students who have any medical situations I should be aware of, see me in private. And what I do is ask them, if you have any kind of medical problem, A, what do you want me to do? And B, do you have something in your backpack or something, a phone number in an emergency, I can get someone from ECC to contact. Luckily, there was never happened that kind of emergency, but I wanted to be prepared because I also had a student who was epileptic. And if something happened, what should I do? Not what you read on the internet. I wanted to know from that person, and I learned. But both of those told me about the dangers of ketosis. And it was interesting because both of those students had something new that I'd never seen before. It was on their arm. They had like a patch with a square box. And guess what? That was their insulin pump. So they didn't have to take insulin shots. And it was quite remarkable. I warned them a couple labs. I got them lab coats because I wanted them to cover that so no chemicals would get on there. But anyways, that's ketosis, and this switches off. Now, for this, you should know what is a sugar, because we use that term a lot. And a sugar is a mono and disaccharide. Therefore, sucrose is a sugar, it's a disaccharide, and fructose and glucose are sugars, they're monosaccharides. You should know sugar is a mono or disaccharide. And it happened this morning, and I warned them, and I'll warn you. Don't forget, Dr. White has the fastest mouse wheel finger this side or the other side of the Mississippi River. And if I ever want to, ask me to go back in the slide if you didn't get everything. Now, I'm going to go through some things. You do not have to copy anything at this point from this slide, but I thought I'd mention this is a structure of glucose. I'm going to talk later that it's in equilibrium with a cyclic form, but this is called D-glucose, and next week I'll explain what the D is for. And just a little background, it's the most abundant sugar in nature. It's also the sugar in your blood. It's an aldohexose, which means it's an aldehyde with 6 carbons, which I won't, and I'll talk about plain polarized light next week. This is glucose. It's a cyclic, can exist as a cyclic monosaccharide. Now, this is D-fructose, and it's a ketohexose or a hex ketose, as ketone, 6 carbons, switches off for this, but it's the sweetest sugar gram per gram. It's much, much sweeter than sucrose, table sugar, which is why when chemists were able to make in a plant this sugar in high fructose corn syrup, it became the sugar of choice in things like foods, including drinks, like if you look at any of your pops, and don't forget Dr. White's from the Chicagoland area, and the stuff in a can or bottle that's carbonated, non-alcoholic, we call pop, not soda. For many years now, the sweetener of choice, because it's cheap and you don't need much, is high fructose corn syrup, fructose. And like I said, it's found in corn syrup. It's cheap. And it forms this cyclic form, which we're going to come back to. Now, this type of ring structure, which shows not only the structure, but the stereochemistry, that's why these lines are dark, and you have the hydroxyl group above the ring and the CH2OH below. These are called Hawthorne structures or projections. And they're two-dimensional structure notation that specifies three-dimensional structure of a cyclic form of a monosaccharide. I tried teaching this a couple of semesters when I first started teaching this long ago, and students couldn't get it. It's really difficult. I even have it at times challenging. And I decided, guess what? I can come up with something easier for the students to understand an important point that I can bypass Hawthorne projections. So I'll never be on the test. All right, switch is on. Let's talk about a couple reactions that you've already learned. And I'm going to go to the whiteboard for this. Oops. Switch is on. If you take an aldehyde or ketone, you learned this for test 2, react it with an alcohol in the presence of acid. Keep your eye on the carbonyl carbon. What's attached to it, R prime or hydrogen, R double prime, has a hydroxyl group, and then the oxygen from the alcohol is bonded to that carbon and the R group. And this is a hemiacetal, hemiketal. Now, use acid to make the reaction, go quicker, because this is a catalyst, and catalysts make reactions go quicker. Now, something I haven't talked about, and that is inter versus intramolecular reactions. How many of you have ever gone on an international flight or been on an interurban train in Europe? What that means is you're going from one international country to another, or interurban from one city to another. And there's the other thing called intra, and that means inside. Now, the reaction I just showed you was an intermolecular reaction between two separate molecules, and you need a catalyst to help bring them together and make it go quicker. Now, if you have both functional groups in the same molecule, they're close together and they can go together and react. Because molecules, atoms to react, have to collide or touch. So I use a catalyst. If I had them in the same molecule, I probably don't need a catalyst. And let's look at that. And this, let's look at and I'm going to draw it not the way my software likes to draw it, but I'll show the aldehyde. And this is glucose. And Mother Nature, in her infinite wisdom, set up a molecule that this is C5, this is 1, 2, 3, 4, 5. Notice you have a carbon with a hydroxyl group, and here I have a carbonyl, an aldehyde. And it turns out when you don't use a catalyst, this is in equilibrium, existence at the same time. Now, to make your life easier, don't tell anybody I'm being nice, this hydroxyl group will attack and bond to that carbon. This hydroxyl group will bond and attack to that carbon, and it forms this new bond, plus opens up to the hydroxyl group. Now, everything else stays the same. If you're not going to react in an area, it's not going to react. So immediately I can do this. All the carbons that do not change and other atoms, I'm just rewriting. Now, this hydroxyl group will be bonded to that carbon. And instead of having students learn how to do a Hawthorne, I came up with this idea that works good. The world's ugliest looking ring and longest carbon-oxygen bond there. And then this will have a hydroxyl group. And this hydroxyl group is this. This oxygen is this oxygen. The first carbon here is this carbon. This carbonyl is this carbon right here. And glucose can form its cyclic form. And by forming the cyclic form, it's set up to make starches. If this didn't happen, we would not have starches in our life or polysaccharides, which means we wouldn't have cell walls for plants. You wouldn't see plants or trees, and we wouldn't be here. Plus, we wouldn't have the good things in life like potato chips, French fries, and pizza, and rice, and other things too, potatoes. But you should know this. On a test, if I give you this structure, you should be able to draw this one. If on a test I draw this structure, you should be able to draw the starting material, glucose. And you should know how to do this. Let me go through this again. The reaction that's going on is this right here. It has an aldehyde or ketone. In this case, it's a ketone. This carbon is this carbon and an alcohol. And here's our alcohol. And just like you see here, the alcohol attacks the carbonyl carbon. This alcohol does the same thing and attacks that carbonyl. And it forms this new bond, which is this bond right here, is this bond right here. This is right here. And this carbonyl is right here. Here's my hydroxyl group and the hydrogen when R prime is hydrogen. And you should know how to do this. And let me just show you, and I'm going to ask you a question. If you don't want to answer, you don't have to. This is how it looks in real life. What I just drew, here's my carbonyl carbon, and that becomes this carbon. This attacks here, which is this bond right here, and this carbon right here is this carbon. Here's my CH2OH. This is CH2OH, but this is the Hawthorne structure, which is easier to draw. This or this. Ooh, I know what I can do, and this is totally anonymous. Instead of asking for what I'm going to send out a question, are you done yet? Do you like my method better than actually learning Hawthorne structure for this reaction? Yes, you do. No, you don't. And you're free to answer. Wow, that was quick. And that's why I came up with it. And somebody who's a purist organic chem, well, it's not the best way to teach it. Yes, it is, because it makes your life easier. But you should know this. Now, this is for glucose, a aldehyde containing monosaccharide, or let's just say for glucose. Now, there's another important, oops, wrong thing. Another important reaction I want to show you. And that is, this is fructose. You don't have to know the structure, but you do have to know the chemistry. And notice it has a ketone. I'm writing it down because I forget, I sometimes get one of the hydroxyl groups wrong on it, and I don't want to do that. And let's go back. This is an equilibrium with this cyclic form. And again, the Hawthorne. Now, guess what I have done? I've come up with the same thing, an easier way for you to understand what's going on. And let's go through that. Now, this is fructose. I can spell it. And let me remind you the reaction you learned for test number 2. Take an aldehyde or ketone, in this case it's a ketone, plus an alcohol. When it's intermolecular, 2 separate molecules, you need an acid catalyst. This attacks that. And you get this. And remember, in this case, our prime is not hydrogen, it's carbons. Well, let's look at this one. Again, Mother Nature only uses this hydroxyl group on C5. 1, 2, 3, 4, 5. And that hydroxyl group, well, first of all, there's an equilibrium. That means it switches back and forth, but it's enough on the right that if this didn't happen, we wouldn't have sucrose, table sugar. I'm glad it happens because I put that in my tea every morning. And this attacks this carbon, which is this carbon, just like here. And once again, you don't break carbon, oops. No, you don't break oops. You get the right color ink. Let's try this again. All right, you have your backbone. Now this carbon right here is going to be this, so I'm going to cheat and put it in. CH2OH has not changed. This hydroxyl group and this hydroxyl group. This one is going to change. I'm just going to leave the hydrogen and the CH2OH. What I've drawn is everything that will not change, I put down. Now we have a carbon here, you don't have to in one here. This has an oxygen, which is this oxygen, and it will bond to this carbon, which also will have a hydroxyl group. And once again, because it's intramolecular, the ketone here and the alcohol here can react without a catalyst. That's why that's the beauty of intramolecular. And if you didn't make this cyclic form here, you wouldn't have table sugar. Because fructose, I'll teach you, is one of the 2 components of table sugar. So I wanted to cover this today so you can practice it over the weekend. On a test, if I give you fructose and this, you should know how to draw the cyclic form my way, which is easier. If I give you this, you should know how to draw fructose. Or I might get nice and just say you just have to put the name down. Same thing with glucose. You might, if I'm real nice on test, you can just put the name down for the starting material. And once again, I'll point out which is easier to understand, going here to my method of drawing the ring, or seeing that this one does the same thing and forms this ring, and this carbon right here was my carbonyl. Here's my alcohol, C5. That means carbon number 5. And which do you like better? Better yet, let me ask again, because I'm in an asking mood. Put yes if you like my way better. This is totally anonymous. Wow, that was quick. And that's why I came up with it, because it helps students. Because when I ask students to draw something like the Hawthorne function structure from this, it was gruesome. It was beyond gruesome. It was not good. So that's why I came up with that. All right, let's move on. Now, quick thing, reduction, see board. Let me go to my whiteboard. For test number 2, you learned the following. Take a ketone or aldehyde reactor with hydrogen and a catalyst. Catalyst can be nickel, platinum, or palladium. You break the pi bond between the carbon and hydrogen, and each one gets a hydrogen. Now, hydrogen, a catalyst, will not react with a alcohol. Hydrogen, a catalyst, will not react with a alcohol, but will react with a ketone and aldehyde. So what would be the product or products of the following reaction? 3 points. Your turn. Keep your eye on where the functional group action is the key one. I see one person done. 2, 3, everybody's done. Let's go do it. All right, What's different here? Well, look for, I've got a, oh, look, carbon double bond, oxygen, hydrogen, carbons. This is an aldehyde right here. Now, this are hydroxyl groups. Let me make that a little better. That's not going to change. So immediately I can write, you're not going to break carbon-carbon single bonds, and the hydroxyl groups won't change. So immediately I can do this. The only thing that will change is this carbon becomes this carbon. It's got a hydrogen, but you break the double bond and you'll form that alcohol. And how many hydroxyl groups are on this molecule? Alcohol. 1, 2, 3, 4, 5, 6. This has got a name, a common name. Sorbitol. And remember, I haven't done it in a while, but why are you learning this stuff? Well, somebody told you had to take my class or organic chemistry, not with just Dr. White, with anybody, to get into a program or get accepted to a school. And but really, why are you learning this stuff? Well, let's go out into the real world now. Sorbitol. It's in a number of things you use. Everybody sees sorbitol on your screen now from Wikipedia. And thank you. If you look over here, here's the structure. Every bend in the line is a carbon. 1, 2, 3, 4, 5, 6. 6, each one has a hydroxyl. You just made it. And sorbitol is made from, they say here somewhere, the reduction of, it can be either biologically, and it's a sweetener, a sugar substitute, because it's low calorie and sweet. And where do you find it? In various over-the-counter medicines and cosmetics. I don't know why you'd want sweet cosmetics. Well, I guess lipstick might use it. But if you go to your big box store or anywhere else, a drugstore, and you buy like over-the-counter cough medicine or other thing, oh, so I'm taking a swig, better take some cough medicine, you'll find on the label sorbitol, and that helps to make it sweeter, and it's more stable than the other sugars. It's not going to, I think, so I don't know for sure, it's not going to be attacked by things that eat sugar and form whatever ickies it could. I like that organic term, ickies. But anyways, it's in a lot of products. Look at labels and you'll see a lot of the stuff I'm talking about are in products you use. It's also, I think, in cough drops, but I'm not sure. Ooh, quick story. Back when I was about 8 or 9, I came down with asthmatic bronchitis one summer. Oh, it was awful. I spent the whole summer in bed, in the house, coughing my lungs out or trying to. My father was a pharmacist, and he brought home a big bottle, a quart bottle from his pharmacy. He didn't need a prescription, of the best cough syrup ever made. And that's called elixir turpentine hydrate with coating. I think I told you about it. It's got coating and alcohol. Oh, it stops the cough and makes you feel real good. All right, let's talk about something switches on but I won't use these words. I'm going to show you something. And that's glucoside formation from monosaccharides. In other words, the cyclic forms something. The glucoside is an acetal or ketal form from the cyclic monosaccharide, and the glucoside is the glycoside form from glucose. Are you confused yet? Don't worry about these first two, but a note from Dr. White to Dr. White. And it is, remember the reaction with methanol. Thank you, Dr. White. I'm glad you told me that, or I might have forgot it. Not, but it's just a safety thing. All right, let me talk about something. And long ago, test number 2, actually not that long ago, you learned the following. Everybody see my whiteboard? I haven't done the thumbs up for a while. Thank you. All right. And you learned this. Take an aldehyde or ketone, react it with two molecules of alcohol, and you get this acetal or ketal. Now, I haven't done this whole semester, and I'm going to do what I call a Cliff Notes version of a mechanism. And if we take the first alcohol and react it with the aldehyde or ketone, you get and you learn this reaction, the hemiacetal or the hemiketal. Now, what I didn't show you when I taught this is, if you take this molecule and react it with the second alcohol, you get this, the hemiacetal or hemiketal. Now, if you notice on the oxygen, both R groups are the same. It's symmetrical. But now I'm going to teach you something new. If you take this, you can react it with a different alcohol. And what you get, this is not replaced with OR prime, it's replaced with the new R group from the new alcohol. And this is the new reaction, or a new wrinkle on this reaction, where now you get an unsymmetrical hemiacetal or ketal. Let's see, I should have done this. This is how I gave it to you. And notice this R group and this R group are now different, where up here they're the same. And you say, well, so what? Well, there's a big so what. And this is also why I came up with my, how should I say this, more pleasant form of the Hawthorne ring. If we look at this molecule right here, it's really this. And this carbon is this carbon. If I react this with my new alcohol in the presence of acid, I'll replace this now with this. Everything else stays the same. Well, if I do the same thing here, this hydroxyl group is this one, and I'll replace it with this. So everything else stays the same. And what I'll do, write this You don't break this carbon-oxygen bond I just drew in. Students like to do that, and I mark it wrong, or they forget to draw it in. Whatever is unchanged, I'm just going to redraw. And the only thing that changes is this, and now becomes this. So I have my oxygen, and then on there will be our triple prime. And that's what you get. And because you can do this, I will show next week, because it looks like I'm just about out of time, that this reaction allows Mother Nature to take the cyclic form of glucose and use this reaction to make all the starches in our daily life, which is a good thing. And with that, first of all, does everybody have this copied down? Who wants to copy it down? Let's wait for Sandra. All right. Wow, we got a lot done today. Thank you. All right, listen carefully. In about 10 minutes or so, I will send out the password for test number 3. You have tomorrow till I think it's either 10 or 11 p.m. AM, 11 a.m. to get it uploaded to D2L. You've already done it like you did for test 1 and 2. Take about an hour and a half to take the test. If you've done the practice problems, you should do good. I hope you do. All right. Don't forget the lab we did yesterday is due Monday. On Monday, I will go through the answers for test 3, but I'll cut them out of the video. But come to my office hour. If you can't, email me and we'll set up a time on Zoom so I can, if you want me to go through them, I will. Also, let me remind you, because I have a lot of personal stuff I got to attend to tomorrow. Normally, I'd spend all day Friday and a good part of Saturday grading. That's going to be switched over. So I promise to you by Sunday, 8 p.m., I will, 1, have your test 3 scores in D2L. 2, I will email you a private, separate email, each one of you, the points for each answer you got on test 3. Also, don't forget, I got a special surprise for you on Monday that I'll put in the assignment area over the weekend. So keep an eye out for it. Oh, that was, keep an eye out for it. But anyways, good luck. Hopefully you don't need good luck on, or you don't need luck on taking the test. And with that, if there are no questions, I'm going to say gehen gesund. But before I do that, the equilibriums I just did with the cyclic form, practice that over the weekend. And also Monday, we'll go through the fats and oils problem set. There's no problem set for polymers, but I'll talk about it. I'm going to get through this stuff probably Monday, Tuesday, and Wednesday and Thursday we'll practice it a lot. Because I know I went through it at a faster pace, but I first wanted to get it out there. And I do this in fall and spring too. Then we'll come back next Thursday and go through it a lot. And if you're, and sometime Wednesday too. With that, oh no, it's really time to leave. With that, gehen gesund, be healthy, have a great weekend. I'll see you Monday. Bye.